Welcome back. Today is lecture 25, Calculus 1, Math 141. We are started with implicit differentiation, just finished with the chain rule. Those two, as far as how I remember them, and I think originally, it's been so long ago I don't know for sure, but I think when I learned them, I kind of learned them together, so it's hard for me to separate them. Our last example, we dealt with a circle, and I wanted to do one more thing, but we were out of time, so let's pick up from that point. So we are in the middle of implicit differentiation. There are a couple of other topics that creep into this, including derivatives of inverse trig, derivative of the inverse sine, derivative of the inverse cosine. I can see the excitement in your eyes. But you just kind of have to hang on to it, contain it, till we get there today. But the reason those are in here is because they require implicit differentiation to get to the derivative. So that's why they're contained in this section. So we did this example. I think the radius was 2. Isn't that the example we did? We solved it for y and found the derivative. We also found the derivative implicitly, and we kind of validated that at a certain point you'd get the same numerical value. I think we put in the 0.4. No, that was the other one, right? We took the xy equals 8, and we validated that. But we solved for y. We got that. We know that's not a function. It's really two functions. The upper semicircle is the principal square root. The lower semicircle is the negative square root. If we find the, let's say, upper semicircle, the equation is the principal square root. And we found the derivative to be, I'm kind of going quickly because we've already done this. I just want to get it to the point where there's one other thing that I wanted to do that we ran out of time for. Somebody go through that process for me. Derivative. 1/2. Negative 2x. Everybody comfortable with that process? Chain rule stuff? So 1/2 of 2, those knock out. So we got, what, negative x over square root of 4 minus x squared. Yep. Is that right? Actually, that brings to mind something else that we need to do before we leave this example, but we'll come back to this. We also took the equation as it was stated originally, which is kind of the whole thing, which is a couple of functions embedded in that description or implicitly described there. So we took the derivative of this implicitly, and this is kind of what we're supposed to do in this section. Derivative of of x squared with respect to x. Derivative of y squared with respect to x. Everybody comfortable with that? Little extra baggage there. That's the chain rule. That would go for anything squared. It'd be 2 times that same thing to the first times the derivative of that thing, and equals 0. So 2y dy over dx equals negative 2x. And I'll put a couple steps together because I'm running out of paper here. What would that be? Negative x over y?
Yes.
So here's the derivative by solving first for y. Here's the derivative by just differentiating implicitly. Aren't the numerators exactly the same? Mm-hmm. Tell me how you know that the denominators are also exactly the same. We did not do this on Friday.
Because y we said was equal to the square root of 4 minus x.
Exactly. See that? Everybody see what Nicole said? Isn't this y? Right? Look back up here. There's y. That's the upper half circle. It's the square root of 4 minus x squared. So this really is the same thing as negative x over y. They are the same. I mean, you can actually justify it from the equations that they are the same. So let's use this one. Derivative of y with respect to x equals negative x over y. And this is the other part of what I wanted us to do to finish this up. So we've got this semicircle. It is a function. Actually, let's just take the whole circle. Because didn't we take the whole circle when we found this? Right? We started with x squared plus y squared equals 4. Found its derivative. We got that. So what is the slope of the tangent at the point 2, 0? How do we evaluate the slope of the tangent at that point?
Put 2 in for the x.
2 in for x and
Solve for
0 in for y. Don't we know the x value and the y value, right? And the derivative is the negative of the x over the y. So none of us like this answer, but it ought to match up with the graph because negative 2 over 0 is what? Undefined. And at that point, 2, 0, which is right there, isn't the slope of the tangent line undefined, right? It's a vertical tangent line.
Yeah.
What about the slope of the tangent line at the point 0, 2? Well, look at the graph. Here's 0, 2. What should the slope of the tangent line be?
0.
It better be 0. Let's see if it is 0 by putting the negative of the x over the y. So that's the slope, negative of the x over the y, which is 0. So at any point on this circle, not just the upper semicircle or the lower one, the whole circle, if you'll take the negative of the x and divide it by the y, you'll get the slope at any point on this circle. Okay, question on that before that gets moved. Yes,
I
Nicole.
have a question about implicit differentiation.
Okay.
If you had like x to the third plus y to the third, when you did that implicitly for the y, how would you write that?
Okay.
dy dx.
Actually, let's take that example and kind of do a sum, and then we'll also do a product.
Okay.
So you want x cubed plus y cubed, right?
Yes.
Equals something, or what else do you want?
Say equals 4.
Okay. So if we want to derive implicitly, which by the end of class today, and then you're doing some problems, hopefully you gain a certain level of expertise with this. And remember, you're deriving with respect to x. So you're going to encounter some non-x things. All you have to do is write them down. When you derive a non-x thing with respect to x, just write it down. Here's an x thing. So we're deriving x cubed with respect to x. What's that?
3x squared.
3x squared. Now, if you think really you're doing something different here than you'd normally do with implicit, go ahead and say, okay, what's the derivative of the so-called inside function, which is x? What's the derivative of x with respect to x? It's 1. So you're technically doing the same thing. Okay, now let's derive y cubed with respect to x. So we have something cubed. What's the derivative of some variable cubed with respect to x?
3y squared.
3 times that same inside variable to 1 degree less. Now we have to take the derivative of that inside variable with respect to x. So this is just a kind of a writing down of the fact that we're deriving a non-x thing with respect to x. We don't know what it is, so we write it down. Over here, we know what it is. We know what dx over dx is. So you can write it down, but you don't really need to. Here, we don't know what the derivative of y. In fact, that's what we're searching for. Everybody okay with that term? It's a chain rule, isn't it?
Mm-hmm.
The inside function is just y. And the derivative of 4 would be 0. And typically at this stage, we want the first derivative, which is y prime, which is f prime of x. In this case, it's dy over dx. It's all of the above. All right, another equation. Same two participants, x cubed and y cubed. This time they're multiplied. Okay, Kent says the product rule. Take me through that first. Actually, let me back up a step. You're correct. Derivative of y cubed, right? He went ahead and was giving that and was correct, but then it'd be what? Y cubed times derivative of x cubed. Product rule. Everybody okay? First times derivative of second plus second times derivative of first equals derivative of 8, which is 0. Good. So that's what he said earlier, and he just said that again. Derivative of y cubed is 3 y squared dy over dx, just like it was up here. There was a separate term up there, but now we're deriving that same separate term as part of the product rule. Derivative of x cubed with respect to x, 3x squared. The process now would be the same. We would solve for dy over dx. So there's some algebra at the end. Seems a little awkward to solve for dy over dx.
Can you do it?
Yes, on this one?
Yeah.
Okay. All right, let's leave this alone, right? It's the term that has dy over dx in it, so I'm just going to put the 3 out in front. And move this term to the other side. It'll now be negative. Right. So isolate the term that has the kind of the intended variable in it. The intended variable to solve for is dy over dx. We've isolated that. Now we want to get rid of everything else. Whoops, not plus. Make that a big times. So those are all gone. So 3 over 3 reduces. It still leaves negative 1 in the numerator. We're going to have an x where? In the bottom. We're going to have a y in the top. So negative y over x. Is that right? They all don't simplify quite to this extent, but there usually is some simplification when you try to solve for dy over dx. So if we knew a point on this curve, let me just see if we can find a point real quickly. How about 1, 2? Is that on this curve?
Yeah.
1, 2 is on this curve. So if we wanted to find the slope of the tangent line at 1, 2, we would put in 2 for the y value, negate it. We'd put in 1 for the x value, throw it in here. What if we had 2 terms that had dy over dx in them? I don't think we've had an example like that, have we? There's a little bit more algebra to that. Let's see if we can get 2 birds with 1 stone here. Not that that sounds very nice. That doesn't sound very nice at all, does it? Depends on how annoying the birds are when you're trying to sleep. Anybody have a WebAssign problem that has, when you were doing the problem, it had dy over dx in it, and then another term also had dy over dx in it? I'll make one up, but if somebody has a web assigned, that'd be even better. Okay, number 2? Okay.
Is this tonight homework?
This is 3-6, which is, this is what's due tonight, right?
No.
What's due tonight?
Chain rule.
Just a chain rule. 3-5 is due tonight. So this is number 2 on the 3.6 homework. X squared. You might have a slightly different problem. You might have the same problem. C is a number. I think we'll see it, thank you, disappear pretty rapidly anyway when we take the derivative. So we've got sum and difference. Within the sum and difference, we also have a product, right? So let's just take them. I think one of the, probably the thing that leads to most errors at this stage of the game for us, Math 141 students, is that you try to kind of go too fast. If it's, just take each term and then analyze what each term is. First term is just x squared. Next term, it is a product, and part of the product is y. So you kind of got to make sure every time you derive y with respect to x, you write that down. You accommodate that. The third term is a function of y. So again, we're deriving a non-x thing with respect to x. We've got to account for that. All right, get me started here.
2x.
2x. By the way, the alternative is to solve this original equation for y. I don't want to do that. I don't think you necessarily would want to do that. I don't even know that it's possible, to be honest with you. So rather than try to do all the background work, which may or may not be even possible, let's just take stuff where it is and go from there. Everybody okay with derivative of x squared? That term's done. Okay, next term is a product.
2, -2.
Actually, let me just put the negative out in front of everything. So we'll just farm out the negative, so everything that follows gets subtracted.
2x.
Okay, 2x is the first term.
Right.
So there's the first term. There's the second term.
2x
So-
times dy over dx.
Good.
Plus y times 2.
Everybody okay with all that? That
Why
should
wouldn't
be the product rule on this term. First, the first is 2x. You could put the 2 with either one. Doesn't matter. But it's got to go with one or the other. 2x times derivative of the second term of the product. The second term is y. So derivative of y with respect to x. Plus second term times derivative of 2x. 2x with respect to x. Right? If you had an issue with that, has it been resolved? So that was the derivative of the second term, which was a product. Third term, what's derivative of y cubed?
3y squared dy dx.
Okay. Now, if you forget the dy over dx, is that going to be incorrect? Yes. You will. From that point in the problem, it's just not going to be correct. Anytime you have y in there, you better account for the fact that you took its derivative and it's not x. Derivative of the constant
0.
is 0, so it doesn't really matter what that constant is. So how is this problem different from the other ones? It has two terms that have dy over dx in it. So like you would do in an algebra problem, you get those two terms together, everything else to the other side, and then see what happens. Let's make sure, though, we take care of the sign, this negative sign. So if I were to leave this term here, this 2x, I want to send it to the other side. So that's negative 2x. This one I left here. We've got minus 2y that needs to go to the other side. So when it goes to the other side, it becomes 2y,
Yes.
right? It's a minus 2y over here. So we subtract that from both sides, or you're subtracting a negative, so in essence you're adding it. And then this term has dy over dx in it, so let's leave it where it is. I bet you that there are some people in here that instead of writing down dy over dx, you're writing down y prime. Is that okay?
Yeah.
It's okay. I like your shirt. I think that you are asking for a problem if you do that. Because you're going to have y's and y primes all in the same statement. This, to me, looks a whole heck of a lot different from y. That looks way too much like y to me. So you can do it. Just be careful that you take care of your y's and make sure they're separate from y prime. Everybody okay with this?
Yes.
What's the next step?
Pull out dy dx.
I'm going to go ahead and put the 3y squared first. Minus 2x. And why did we factor out dy over dx?
So you can divide by.
So we can divide by this. Everybody take it from there? This is a jump start.
Wouldn't it have helped you, though, to not move it around? So then when you divide, you can cancel out the two x's.
Can't cancel that out.
They won't cancel out because they're part of the, let's finish, okay? Because you may not be the only one where that is tempting. So there's dy over dx. Can we cancel negative 2x over negative 2x?
No.
No. Why not?
Because it's in minus and plus sign.
Because it's not multiplication and division. It's not a factor. Negative 2x is not a factor of the numerator because the numerator has two terms, right? Negative 2x is not a factor of the denominator. So as tempting as those are to strike through them, that you can't reduce them. They're attached. This one's attached by addition to 2y. This one is attached by addition to 3y squared. It's got to be product and or quotient to be able to kind of knock out like terms, numerator and denominator. Is that all right? Problem 2 on the, is everybody's problem the same, by the way? Does anybody have a printed copy that's the same as what Talissa gave me? No? If it's not that problem, it'll be something very similar to that, so the procedure will be the same. Here's a unique equation. This is called an asteroid. Okay, is the official name of this function.
Are those powers two?
Powers, 2/3, yes. The sketch of this, well, you can think of some points that would be on this that are pretty obvious. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. All 4 of these points are on here. Now, let's make sure. Don't just take my word for it. So when you take something to the 2/3, what do you do to that? What's the first thing you do to it? Cube root. So this is the root index, right? We're going to take the cube root of the value here, and then once we take the cube root of it, what do we do to the result? Square it. So it doesn't matter if you put in 1 or negative 1, as long as the other entry is 0. If you put in 1 or negative 1, you're going to take the cube root of it, which is 1 or negative 1, and then do what to the result? Square it. So it is good. All 4 of these points are going to work. Now the rest of these, if you would plot this, the rest of this graph looks something like this. So suppose we want the equation of the tangent line at that point. Negative 1/8, 3 square roots of 3 over 8. That is a point on this graph. Let's see, negative 1/8, somewhere up in here is the point we're talking about. The tangent, it would be, my diagram's not the greatest here. There's the tangent line, right? Oh, that's a good point to bring up. Yes. The tangent line, although it's tangent to the curve in this area, it is permissible for it to intersect somewhere else, but it's tangent in this general vicinity. That's very common for a tangent line to hit the curve elsewhere. Doesn't make it not tangent, it's just tangent at that general area. So we do have in this vicinity, it is tangent. It so happens that it's not a function, which creates a problem, and it hits it somewhere else. But it still is the equation of the tangent line. That's actually an excellent point to bring up. If we want the slope of the tangent, we want y prime, we want dy over dx. And here's our kind of interrelationship of x and y. So what's the derivative of x to the 2/3? Sounds like we got a consensus on that. What's the derivative of y to the 2/3? Good. We're deriving that inside function is y, so that's our final piece, is deriving that inside function, dy over dx, equals derivative of 1, which is 0. You would not believe the number of times, and I've been teaching a lot of years, that I've seen the derivative of 1 is 1. Okay? Not true. So you're doing all the hard work correctly. Remember to do the easy stuff correctly as well. Derivative of 1 is 0. All right, this term, keep it here. This term, send it to the other side. So if this goes to the other side, it's positive here. It becomes negative on the other side. Yes, we'll do that. As long as we have kind of all products and quotients at the end, we'll kind of move terms where they need to go. So let's divide. And you can do that anytime. Just be careful that you don't do all the hard stuff correctly and then mess up algebraically. So 2/3 and 2/3 reduce. So we've got at this stage negative x to the negative 1/3 over y to the negative 1/3. So what were you wanting to do, Nicole?
I was just saying it would be negative 1 over x cubed, and then
1 over x cubed?
It would be negative y,
Negative
or
y
cubed root of y.
Well,
Cube root, right?
Yeah.
1 to the
Negative
negative
10,
1/3
yeah.
would be cube root.
Yeah.
If everything is multiplied and or divided, everybody convinced that's the case with this?
Yes.
Yeah.
It's all multiplication. Isn't it legal to take this thing with the negative exponent, send it to the denominator, and now it has a positive exponent? And the same thing with this.
Yes.
It's all product and or quotient. So this has a negative exponent in the denominator. If we send it to the numerator, it would have a positive exponent. Is that equivalent? And y to the 1/3, if we have to put a value in, which it looks like we do, right? Back up here, we're supposed to put in a certain x value and a certain y value. That doesn't look real delightful to me, but we don't necessarily have to simplify. We can punch some buttons on the calculator and see what happens. So we have dy over dx equals negative cube root of y over cube root of x. Y to the 1/3 over x to the 1/3. So that point of tangency, don't ever accuse me of choosing all the easy problems. Okay, this gets kind of ugly right here. But we do need to know the slope at this point, right? And what do we typically do at this point in the problem?
Plug in your x and y.
Plug in the x and y. Or before implicit, before chain rule, actually before implicit, we just plugged in the x, right? I wish that were the case. But we plug in -1/8. Up here we've got a negative cube root of, this is the bad value, 3 square roots of 3 over 8. Man, maybe not so bad. Numerator's negative. It's the stubborn one, so let's leave it alone for a second and do the easy one. So what's the cube root of -1/8? What do you take times itself and then times itself again to get -1/8? -1/2. So that's not too bad. This one's not awful if you just stop and think about it. 3 square roots of 3. Think about something that could be used as a factor 3 times to get that. And then denominator, something that could be used as a factor 3 times to get 8.
2 for the bottom.
Good. Eric, square root of 3. Isn't the square root of 3 cubed 3 square roots of 3? Right? Square root of 3 times square root of 3 times square root of 3. Those two give you 3, and you have an extra square root of 3. That's exactly what that is. So the cube root of 3 square roots of 3 is the square root of 3. The cube root of 8 is 2.
And it's negative.
Right, we negated it, right? This,
because of the bottom.
right, this right here was the cube root of a positive number, so it's positive. This down here was the cube root of a negative number, so it was negative. But we still have that negative floating around the numerator from that expression right there. So the slope, if we multiplied the numerator by +2 and the denominator by +2, what's the end result?
Square root of 3.
Good. So it looked pretty bad there for a while, but it's not all that bad. Would it be wrong if you decided not to do battle with 3 square roots of 3 over 8? You got a decimal equivalent,
Yes.
took the cube root. You would have probably gotten very, very close to this, which is about 1.732. And WebAssign's probably going to take it. And I know that you know what you're doing, so that's fine with me too. But go ahead and give it a chance first to see if you can find an exact value. This is slightly better than 1.732 because it's exact. This is the easy part of the problem. The hard part's already done. We just plug in the values that we have. Y minus the known y value. There's the known y value. Equals slope, positive, square root of 3, x minus the known x value. Now for WebAssign, you're going to have to go further than that. For a test or quiz, you can stop there because I know that you know what you're doing. Is that okay? Alyssa?
Why did you have to change when you had it, like, before you changed it to the cube root, why did you have to change it to cube root? Like, why couldn't you leave it 1/3?
You can.
Okay.
And if you want to use your calculator and raise something to the 0.3333 or to the parenthesis 1/3 parenthesis, that will still work. But if you want to kind of think through it, and you're probably going to be able to think through it better if you call it a cube root, because you're searching for the cube root of -1/8. Probably it's going to come a little quicker to you than if you said, I've got -1/8 to the 1/3. But they are both the same. Anything else before we leave that? Okay? Okay to move it? Got to have our daily dose of trig here. And a little exponential stuff in here at the same time. Let's find dy over dx. And my wish is that I am needed less and less as the process goes. Somebody take over.
You can separate.
What is that?
Can't you rewrite the cosine?
You could. Do we want to write that as cosine of x minus cosine of y? No. No, you can't do
The other
that.
way. No,
Derivatives.
can't you? Isn't there like an equation for that?
That's not the cosine of x minus the cosine of y, is it?
No.
Not unless they changed the rules over the weekend. Didn't let me know.
No, isn't it like cosine? Never mind.
Negative sign.
Negative sine of x minus
There we go. This is the cosine of something. We don't like that something as well as we like other somethings, but it's the cosine of something. What's the derivative of the cosine of something? Negative sine of that same thing times the derivative of that thing. Does that work?
Right.
That's really kind of chain rule. We haven't really done implicit yet. We had the cosine of something. Derivative of the cosine of something is negative sine of the same thing. Then we have to kind of look inside, take the derivative of what's inside. Right side is a product. Tell me what to write down.
X times e to the x plus 1. E to the x times 1.
Got a consensus on that? Right? Product rule, first times derivative second, so that must be the derivative of the second. Plus second times derivative of first, that must be derivative of the first. So no implicit yet. Separate that. That's kind of an expression in and of itself. What's the derivative of the thing that was kind of inside here, this x minus y? What's derivative of x minus y?
0.
Derivative of x is 1. Derivative of y is 1 dy over dx, right? We're deriving, here we were deriving an x thing with respect to x, 1. Here we're deriving a y thing with respect to x, so we have to write that down. So there's where the implicit part comes in on this problem. So we want to isolate the term that has dy over dx in it. That's this term. So how do we get rid of the other term? Divide by it. Now, we're not done, but we have the term that has dy over dx isolated. Everybody, do you feel confident you could take it from here?
Mm-hmm.
You would still do the same thing. Now isolate this part of the expression by what? Subtracting 1 from both sides? And then dividing both sides by negative 1. So from here, the process is the same as it has been to this point. I think I'm going to skip orthogonal trajectories today and come back to that because I'd like for us to get, I don't know, we might have time, but I'd like for us to make sure we get inverse trig first, and we'll fill in with orthogonal trajectories next class. So we're going to have some inverse trig, inverse sine. I mean, you've got this stuff on your calculator. Inverse cosine, inverse tangent. And I don't think we're going to have much need for the other inverse trigonometric functions. So we've already done the derivative of y equals sine of x. Now we want to derive the inverse remember to get inverse, you'd switch x and y and solve for y. Well, what is y here? That's right. Y is the angle you're taking the sine of to get x. Is that correct? So y in this side is the inverse sine of x. So you've literally interchanged the roles of x and y. So we know how to take this derivative. Derivative of sine is cosine. End of problem. What we're trying to accomplish now is to find y prime when y is not sine of x, but inverse sine of x. So let me make sure we're agreeing on this. This statement and this statement are exactly the same. Is that true? Equivalent statements? Y is the angle you take the sine of to get x. That's exactly what this says. Y is the angle you take the sine of to get x. So instead of using the one that's solved for y, because we don't have the ability to do that yet, let's use this one, which is exactly the same thing. Derive implicitly, which is why it's in this portion of the textbook, and let's find dy over dx. Excuse me. So let's take the inverse sine function, solve it. We've got x equals sine of y. I'll do the left side. I'll do my part. What's the derivative of x with respect to x? That's 1. Now you have to do your part on the right side. What's the derivative of the sine of something? Cosine of that thing. Are we done?
No.
Good, because we're now, what is the derivative of that thing? Derivative of that thing, it's a y thing. Derivative of that is dy over dx.
So y thing.
Divide both sides by cosine. That is a correct answer, but it is not the answer that you're going to use 99% of the time. Because we expect an answer in terms of x, right, when we see dy over dx. Now, if you had a point, you'd just plug in the y value and take the cosine of it, and that'd be the slope. So that's very rare when that happens. Right now, we're trying to derive this in terms of x in general. So we need to take that statement as well as what we started with. We started with, there was our statement. We didn't use that. We used something that was equivalent to that, which is that. And we found that dy over dx is 1 over cosine y. Let me draw a diagram for this statement right here. Illustrating this with some just right triangle trig. I want to take the sine of the angle y, so I'm going to make y one of the acute angles. Kind of cute, isn't it? So what should the sine of y be according to this statement? The sine of y better be x, right? So can I label, here's y, can I label opposite x and hypotenuse 1, and does that accomplish what I want to accomplish?
Yes.
Is the sine of y equal to x on this diagram? So do we have enough to find the third side? If you know two sides of a right triangle, what can you do to find the third side? Pythagorean theorem. 1 squared, excuse me, whatever this side squared plus x squared is equal to 1 squared, right? So this thing squared is 1 minus x squared. Question mark is square root of 1 minus x squared. Now, using that diagram, can we rewrite our answer to 1 over cosine y? What is it? Let's pick it off of this diagram. What's the cosine of y? Wouldn't it be adjacent over hypotenuse?
Yes.
Is that the cosine of y? I hope it is from that diagram. And something over 1 is just that. Okay. So I know a lot of you have had some calculus. There's a chance that you've had some calculus and not inverse trig. Make sure that you jot that down. If this is our original function, there is the derivative. And it is in terms of x with respect to
Memorization
x.
thing?
Pardon?
Is this just like a memorization thing?
Yeah, probably. Now, I forget this some, so she says, is this just a memorization thing? Probably. But what's nice to know is that if you don't use this all the time, then to have a way of getting it. So y equals inverse sine of x, if you actually write it out in terms of a sine function and not an inverse sine function, you've got a way to get the answer. And I find myself doing that a lot, actually, is rewriting it, deriving it. It's not that complicated. I mean, look at how many steps we had back over here. Derivative of this side, that's a toughie, 1. Derivative of sine of y, cosine y dy over dx. You can get there in a matter of, what, 25 seconds if you happen to forget. But truthfully, it's probably one of those memorization things. All right, let's do 2 others real quickly, and I think we'll stop there. Let's do inverse cosine. How can we rewrite it? We don't even know what this is, right? So let's see, if you happen to forget it, how can you come up with an answer in a short amount of time? How can I rewrite that?
X equals cosine y.
X equals cosine y, same statement. Let's take the derivative. Derivative of x is 1. Derivative of cosine of y is,
Negative sine y.
give me the rest,
dy dx.
dy over dx. So dy over dx is what?
Negative sine. 1 over negative sine.
1 over negative sine?
Yeah.
I'm going to call it negative 1 over sine. Let's get a diagram from that statement. How do I label this triangle? I need to label it so that the, what? Cosine of y is x. What's cosine? Adjacent over hypotenuse, right? Is that true? Is the cosine of y equal to x on this diagram? What's the third side?
Squared over.
Square root of 196.
Okay. So here's our answer. Should be negative 1 over the sine of y. Sine of y ought to be opposite over hypotenuse. So how does the derivative of inverse sine differ from the derivative of inverse cosine?
Negative. It's just negating. Yeah.
Just a negative sign. But isn't that familiar, by the way? And we have that negative sign difference there. And this ought to go real quickly, too. In fact, this is probably the quickest of the 3. Y equals inverse tangent. So if we rewrite that, x is tangent y. Take derivative of both sides. Derivative of x is 1. What's derivative of tangent y?
Secant x,
Secant squared y. We're deriving a y thing with respect to x. So 1 over secant squared y equals dy over dx. What do we do now? Get a diagram from our original statement. Y is one of the acute angles. Doesn't matter which one you label it. But from y, what do we know? We know the tangent of y is x.
Opposite over adjacent.
Opposite over adjacent. X over 1 is x, right? What's the hypotenuse?
X minus, or 1 minus x.
1 squared plus x squared is this squared, right? So it's the square root of the sum of their squares. So here's our answer. dy over dx is 1 over secant squared. Gosh, what's secant? Reciprocal of cosine, right? So cosine would be adjacent over hypotenuse, so we want hypotenuse over adjacent. Are we in trig overload yet? So the numerator's 1. This is something over 1, so it's just that something, and it's a square root squared, which is so there is derivative of inverse tangent. Actually, we probably end up using this one a whole lot more than derivative of inverse sine or derivative of inverse cosine. We're out of time. I will see you tomorrow.
No class Thursday. Thursdays?
Yeah.